we'll be diving into Neural Radiance Fields, NeRF, a deep learning model that generates photorealistic 3D scenes from 2D images. The key idea behind NeRF is to predict the color and density at any given point in a 3D scene, which allows us to render views of that scene from new perspectives, as if we were actually looking around in it. Let's explore it in 4 parts. The Neural Radiance Fields architecture. How does volume rendering work in NeRF? The volume density profile affect the final rendered image. The positional encoding play in NeRF's volume rendering. Now let's explore how Neural Radiance Fields architecture achieves this. The first, input data. NeRF starts with 2D images of a scene, and alongside these images we also need the camera poses. A camera pose gives us the position and orientation of the camera when it captured each image. These images provide all the visual information the model needs to learn from. The second, ray sampling. NeRF works with rays in 3D space. Imagine a ray as a straight line that extends from the camera's position through a pixel and into the 3D scene. For each pixel in the 2D images, a ray is cast into the scene. Then, NeRF samples points along these rays at regular intervals to gather information about the scene's properties, like color and opacity. The third, scene representation. To represent the scene, NeRF uses a fully connected neural network, also known as a multi-layer perceptron, MLP. This network predicts 2 key things: color RGB at each sampled point, and density, which tells us how opaque or transparent a point is. This MLP is trained to output these values for each point along the rays, capturing both the geometry and lighting of the scene. The fourth, MLP network architecture. Let's look at how the network works. 1. Inputs. The MLP takes in 2 things: the 3D coordinates of the point along the ray, and the 2D viewing direction, basically where the camera is looking. 2. Network structure. The MLP is typically made up of 8 to 10 layers with activation functions like ReLU, and then an output layer that gives us the RGB color and density values at each sampled point. The network's job is to learn how the 3D position and the camera's viewpoint together determine the color and density at that point. The fifth, volume rendering. Once we have these predictions for each sampled point along the ray, the next step is volume rendering, which is how we get the final color that we see in the image. Here's how it works. The model gives us color and density at each point. Transmittance tells us how much light gets through as the ray travels through the scene. It's based on the accumulated densities. Then radiance accumulation. Using color and density, NeRF combines the contributions of all sampled points along the ray to compute the final color we see at that pixel. This includes how light interacts with the scene, like scattering or absorption. The final color is calculated using this formula, where Ti is the transmittance at the eye point, sigma I is the density at the eye point, delta Ti is the distance between the samples, Ci is the color at the eye point. The sixth, training the model. To train the model, we compare the rendered 3D scene with the original 2D images. The model is optimized using a loss function, typically L2 loss, which measures the difference between the rendered and actual pixel values. Using backpropagation, the MLP learns to reduce this error and improve the accuracy of the rendered views. In summary, Neural Radiance Fields represents a huge leap forward in the way we can generate 3D scenes from 2D images. By leveraging deep learning, NeRF can produce highly detailed photorealistic renderings, capturing complex light interactions and geometric details. Now, let's dive into how volume rendering works in Neural Radiance Fields, and how this process enables the generation of photorealistic images from 3-dimensional scene representations. NeRF uses a continuous volumetric representation of a scene. This means that for every point in 3D space, there are 2 key values: color and density. These values help the model simulate how light interacts with the scene, allowing it to create new views of the scene by integrating information along rays that are cast from a camera. Let's break it down step by step. The first, ray casting. The process starts by casting rays from the camera. For each pixel in the output image, a ray is cast from the camera's position into the 3D scene. Mathematically, a ray can be represented as where O is the camera origin, the starting point of the ray. D is the view direction, the direction in which the ray is traveling. T is the parameter that varies along the ray. As the ray moves through the scene, we sample multiple points along the ray at intervals. These points are either fixed at regular distances or adjusted adaptively depending on the scene's complexity. The second, neural network inference. At each of these sampled points along the ray, we input the point's 3D coordinates into the neural network, which transforms them into a higher dimensional representation. This transformation helps capture high-frequency details of the scene. For each sampled point, the network outputs color, RGB, the color at that point in space, and volume density, a scalar that tells us how much light is absorbed or scattered at that point, affecting the opacity. The third, volume density and color accumulation. We use the volume density to determine how much light is absorbed as it travels through the scene. The goal is to accumulate color and transparency as the ray progresses through the medium, which is done using classical volume rendering techniques. The key here is the transmittance function, which tells us how much light has passed through a point without being absorbed. It's defined as. This function helps us calculate the accumulated color along the ray based on the density at each sampled point. The accumulated color for the ray is given by the integral, where T is the transmittance, how much light survives up to point T. Sigma is the density at point T, controlling light absorption or scattering. C is the color emitted at point R, based on the view direction D. The result is the final color along the ray. The fourth, rendering equation. The final color for a pixel is obtained by summing contributions from all sampled points along the ray, where Ci is the color predicted by the neural network at sample I. Delta Ti is the distance between two adjacent sampled points along the ray. This equation calculates the accumulated light as it passes through the scene, considering both color and density at each sample point. The fifth, differentiability and optimization. One of the key features of NeRF is that the volume rendering process is differentiable. This means that we can backpropagate gradients through the network during training. As a result, we don't need a fully detailed 3D scene. All we need are a set of images with known camera positions. This makes NeRF particularly efficient for training from sparse input data. The sixth, final image synthesis. After processing all the rays corresponding to each pixel in an image, NeRF synthesizes the final 2D image. Each pixel's color is determined by the accumulated light along its respective ray. This results in a photorealistic rendering of the scene, capturing complex details like lighting and shading. To summarize, in NeRF, volume rendering involves casting rays through a 3D scene, sampling points along each ray, and predicting color and density values at each point using a neural network. These values are integrated along the ray to produce the final pixel colors. By doing this, NeRF can generate realistic images from new viewpoints, capturing detailed lighting effects and scene geometry. The differentiable nature of this process allows NeRF to optimize efficiently, even with sparse input data. Now let's explore the importance of the volume density profile in neural radiance fields and how it plays a critical role in determining the quality of the final rendered image. The first, opacity and light absorption. 1. Volume density. The volume density at each point along a ray represents how much light is either absorbed or scattered at that particular point. If the density is high, it means the material is opaque and light will be absorbed more. In simpler terms, higher densities block more light, making areas darker in the final image. 2. Impact on rendering. If the volume density is incorrectly defined or not tuned properly, parts of the scene might appear too transparent or too opaque. This leads to unrealistic results, such as objects looking either too see-through or too solid. Getting this right ensures that light interacts with the scene as expected, improving the realism of the rendered image. The second, color accumulation. 1. Color contribution. As a ray samples different points in the scene, The color at each sampled point is influenced by how much light is transmitted from previous points along the ray. This transmission is governed by the transmittance function, which is directly linked to the density at each point. 2. Resulting image quality. The way density varies across the scene impacts the smoothness of the color transitions. If the density profile isn't smooth or consistent, you might see harsh or unnatural color shifts. A well-defined profile creates more natural, visually pleasing transitions in color, enhancing the overall rendering quality. The third. Depth of field and scene complexity. 1. Depth perception. The volume density profile affects how depth is perceived. By simulating effects like fog or haze, which are materials with varying densities, NeRF can make objects appear closer or further away. This adds realism to the scene by creating a sense of depth. 2. Complex scenes. In complex scenes with overlapping objects, a well-defined density profile helps manage occlusions, where one object blocks another. This ensures that objects are correctly rendered in relation to each other, which is crucial for scenes with intricate geometry or a lot of overlapping structures. The fourth. Sampling efficiency. 1. Adaptive sampling. NeRF uses the volume density profile to guide adaptive sampling. In areas with high density, where light absorption or scattering is greater, the model will take more samples to accurately capture the effect. In areas with low density, fewer samples are needed. This optimization reduces the computational load while still maintaining the quality of the image. 2. Early ray termination. If a ray encounters a point of high density, it might absorb enough light, making further samples unnecessary. This is known as early termination. A properly defined density profile allows the model to terminate rays early, which reduces the number of unnecessary calculations, speeding up the rendering process without losing image quality. In summary, the volume density profile in NeRF plays a crucial role in how light interacts with objects in a scene, influencing both opacity, how light is absorbed or blocked, and the smoothness of color transitions. It helps simulate depth and manage occlusions in complex scenes. By optimizing sampling efficiency and reducing visual artifacts, a well-defined density profile ensures high-quality, realistic renderings. Now let's break down the importance of positional encoding in neural radiance fields, particularly in how it enhances the volume rendering process. Positional encoding plays a key role in allowing NeRF to capture complex details in 3D scenes, which is essential for producing realistic and detailed images. Here's how it works. The first. Mapping to higher dimensional space. 1. Purpose. The main job of positional encoding in NeRF is to transform the raw three-dimensional coordinates and viewing directions into a higher dimensional space. This step is crucial because it enables the model to capture finer details and more complex variations in the scene, which are vital for realistic rendering. 2. Mechanism. Rather than using the raw spatial coordinates, like XYZ directly, NeRF applies a positional encoding function. This function uses sinusoidal functions to generate a higher dimensional representation of the input data. This mapping is important because it helps the network learn complex patterns and high-frequency features which are essential for rendering scenes with intricate details from various viewpoints. The second, improved representation of high-frequency details. 1. High-frequency variations. Standard neural networks tend to struggle with capturing high-frequency details, like sharp edges or small-scale variations in geometry, because they naturally focus more on low-frequency patterns. Positional encoding overcomes this limitation by injecting high-frequency components into the model, allowing it to better capture subtle variations in both geometry and appearance. 2. Impact on image quality. With this enhancement, the model can better represent these fine-grained details, which translates to sharper and more detailed rendered images. As a result, the output images look more realistic, maintaining consistency and detail across different views of the scene. The third. Facilitating optimization. 1. Parameter optimization. Because positional encoding maps the 3D coordinates to a higher dimensional space, It helps the network optimize its parameters more effectively during training. This richer representation space allows the model to converge faster and better, fit the training data, leading to improved performance overall. 2. Studies show. Studies have shown that models that include positional encoding outperform those that don't, particularly when dealing with complex scenes that have significant variation in detail. This suggests that positional encoding is crucial for handling intricate geometries and producing more accurate results. The fourth. Handling view dependence. 1. View direction encoding. In addition to spatial coordinates, NeRF also encodes the viewing direction using positional encoding. This is essential because it allows the model to capture view-dependent effects, such as reflections, refractions, and lighting changes based on the viewer's perspective. These effects are key to achieving photorealistic renderings. 2. Enhanced scene understanding. By encoding both the position and the view direction within the same framework, NeRF can better understand how light interacts with surfaces from different angles. This deeper understanding helps to create more accurate and realistic visual outputs, enhancing the overall image quality. In summary, positional encoding is a crucial component of NeRF's volume rendering process. It allows the model to represent high-frequency details, optimize the training process for faster convergence, and effectively handle view-dependent effects. By transforming input coordinates into a higher dimensional space, positional encoding significantly improves the quality and realism of synthesized images, especially for complex 3D scenes.